All right, on to part two, putting it all together. So on part two, we are putting together our knowledge of transformations, our knowledge of exponent rules. Do you guys remember learning exponent rules relatively in Algebra 1? Like if you are multiplying two exponents, that means you're adding their powers. If you're dividing two exponents, that means you're subtracting their powers. Any of that ringing a bell? Okay. If you don't remember, above the turn-in box, there's a little Algebra 1 reminder poster of exponent rules. You can always look at it, take a picture of it, and whatnot. I can't reach you. We're on to the next. Mm-hmm. We're on part two now. Welcome back. All right. So here we go. We're going to review one of your exponent rules. So the exponent rule that we're going to review is our, I want to say, power rule. I'm not really great at the names, but I remember the process. Okay. So if you have an exponent, a base to a power, and then it's raised to another power, all you're doing is multiplying those two powers. Do y'all remember that rule from X? Is that sounding and looking familiar? That's the review. That's the one we're focused on for this part of our notes. Okay. So the reason why we're doing this is because it asks us to determine if the following equation is a growth or a decay. In order to determine if it's a growth or decay, we need to separate the variable from the number. Okay. And we can separate the variable from the number by using this rule here. This rule tells me that I can separate using parentheses, right? If I can combine using parentheses, then I can go the other way as well. So here we have e to the 5x. I need to separate the 5 from the x. So in order to separate, I'm going to write it as e to the 5 to the x. What this now allows me to do is just to look at my base as all of e to the 5. So e to the 5 is my base. E to the 5, and the question is, if I'm a growth, remember that means we are greater than 1. If I'm a decay, I am less than 1, but greater than 0, right? But essentially just less than 1 we're focusing on. So e to the 5, is that going to be greater than 1 or less than 1? It's going to be greater than 1 because e to the 5 is greater than 1, then this is a growth. Was that terrible? Okay. Remember, E is roughly 2.713, right? And if I have 2.713 times 2.713 times 2.713 times 2.713, that's going to be a larger number, right? Okay. All right. The next exponent rule that we're reminded of here is our negative exponent rules. If you have a base to a negative power, what that means is that it actually belongs in the denominator. Do you guys remember that rule? Your negative exponent rule? So we're going to be using a combination of these two rules to evaluate whether this is a growth or a decay. Okay. So the first thing we need to do is separate our numerical from our variable. So we have e to the negative x1 half. E to the negative x over 2 is the same thing as e to the negative 1 half to the x. Dividing by 2 is the same thing as multiplying by 2. Okay? Because your exponent is negative, where does it actually belong? In the denominator. So e to the negative half actually belongs in the denominator. So it's actually 1 over e to the half to the x. Is this value greater than 1 or less than 1? It's going to be less than 1. So because it's less than 1, then we know that this is a decay. So when I say putting it all together, we're putting all of our prior knowledge into a little basket. Do you guys remember those exponent rules? Vaguely sound familiar? Like something you've learned before in your life? Ringing a little bit of bell. May have some cobwebs on it. Okay. Next, we're going to still keep using, we're going to keep refreshing on our exponent rules. We're also going to be talking about our translation rules. So when I look up here and I have to describe the translation that's taking place here, looking at A, f of x equals e to the x plus 3, what is my translation? Three units left. Remember, our x's are pliers, so I want to say right, but it's actually to the left. So how it currently looks, this is 3 units left. On that same token, look at here, f of x equals e to the x minus 5. That means that this is what? 5 units to the right. Okay? Now it wants us to describe it as a dilation. You're probably like, describe it as a dilation? How am I going to describe this as a dilation? Well, in order to describe this as a dilation, we have to rewrite it. And we're going to rewrite it using our exponent rules of product and quotient. Okay? Your exponent rule of product says that if you have two bases, base m times base n, when you're finding their product, it becomes base of m plus n. Does that make sense? Y'all remember that? So what that means is that I can actually take my plus and separate it into two different two factors. So instead of this just being e to the x plus 3, this is e to the x times e to the 3. So it went from being a translation to now being a dilation. Because I have a factor in front. I have an a now instead of a c. If it bothers you that the a is there, then look at it as y equals e to the 3 times e to the x. Remember, for multiplication, order doesn't matter, right? 2 times 3 is the same thing as 3 times 2. So now I'm looking at my a value. And my a value is it greater than 1 or less than 1? It's greater than 1, right? Because this value is greater than 1, I now know that I have a vertical stretch by e to the 3. I forgot the word factor. Pretend that says factor in there. By a factor of e to the 3. It's a vertical stretch because this value is greater than 1. And we're going to look at it in Desmo so you can see what I mean when I'm like, oh, they're the exact same. Okay? On B, we're going to review our quotient rule of exponent, which means if I have b to the m divided by b to the n, that equals b to the m minus n. So I can condense or I can expand, and it's going to change how it looks. So in this case, it's already condensed, so we are expanding. Now, division is different. Order matters in division, right? So your first term is your numerator. Your second term is your denominator. So this becomes e to the x divided by e to the 5. First term is in the numerator. Second term is in the denominator. So in terms of a function, we have y equals 1 over e to the 5 times e to the x. And now this is my a. And I'm asking myself, is this a greater than 1 or less than 1? It's going to be less than 1. And because it's less than 1, it's going to be a vertical what? A vertical compression. So it's a vertical compression by, the word is supposed to be a factor in there, and I didn't write it last time. by a factor of 1 over e to the 5. So exponential functions are a little tricky boogers that they can shapeshift on us. So let's look at how that looks on a graph. So initially, all of them start off as e to the x, right? That's the parent function, right? And we're going to transform it based on what was given. So the first transformation we had was e to the x minus 3. Was it? Nope, power. Forgot. In decimals, make sure you use parentheses when you're putting more than one thing as a power. Okay? And it shifts my red to the right, correct? Which we said was going to happen because we knew that because we're geniuses. Okay? Then we said, okay, well, because of exponent rules, this can be rewritten as a dilation. And we ended up with e to the 3 times e to the x. That's about right. I'll just let you, there we go, plus, fixed it. And what do you notice? So there's the blue, and what did the green do? It's the same, because all I did was manipulate that function. And that's why you can read an exponential as a translation, or you can read it as a dilation, because they're equivalent forms of each other. Okay. And that's why that works. Okay. The same thing would happen with the 5. So if I put this in as -5, and I came over here and I put this as 1 divided by e to the 5th. Notice again, here's the blue. And then when I graph the green, it overlaps it because they are equivalent. They are the same. Okay. So depending on what it's asking you, if it's asking you to describe the translation, describe the translation. If it's asking you to describe the dilation, then you should be able to do one or the other, or and go back and forth. And that's the shape-shifting exponentials. All right. Up next, exponentials continue to shapeshift because any exponential function can be expressed using other bases. How do you express it using other bases? Is by remembering what is the inverse of an exponential. What's the inverse of an exponential? A log function, right? And you can express any exponential as whatever base you want as long as you're using the log of that base to do so. Okay. And so we're going to start here. It wants us to express 3 to the x with the base of e. So essentially we want 3 to the x to equal e to the kx. If I want them to be equal, my k and my x look the same. Sorry. I'm going to have to use log of whatever base I want it to become. And I want it to be a base e. It's her. She was kind of ugly. Couldn't deal with her. Okay, so we're going to take log base e of the left equals log, it's a little e, and I know it looks like loge, of e kx. What this does is it introduces a new exponent rule, exponent rule. Your power of your argument when you have a log and an exponent becomes your coefficient. The power of your log becomes your coefficient. So we end up with log base e of 3 equals k times x of log base e of, and this is my favorite part, eliminate. Do you guys remember that if you have the same factor on the left and the same factor on the right, what do they do to each other? They cancel out. So the x's are gone. When you have a log of the same base and same argument, guess what they also do? They cancel each other out. So all you're left with is log base e of 3 equals k. So now we know our k value. which means that we now can write the model that fits this. So what would be the equivalent form? We're going to call it g of x. G of x would equal e, and I put my x in front so that it doesn't get lost in my log. E to the x of log base e of 3. And that would be the equivalent disguise. Okay. Now, after going through these steps, do you see any shortcut, any pattern, anything that looks like, oh, this will make it so much easier? I see now what they did. I'm not going to tell you it, so I'm asking if you see it. Okay. Well, you're going to do the last one and either do it the long way, or if you recognize the shortcut, then just write your answer. Okay. So you're doing this one. And again, if you recognize the shortcut, then you're going to just write the answer. If you don't recognize the shortcut, then you're going to go through the same process that we did here. And go. All right, let's see how we did. So, up here again, we discussed that if I want to change the base of my exponential, I have to take the log of whatever I want that change to be. And I want the base to become e. So I'm going to take log base e of the left, and I'm going to take log base e of the right. Because I'm taking the log, that means my powers become my exponents. My powers become my exponents. And I'm left with x log base e of 2/10 equals kx log base e of e. Favorite part is canceling out. I got an x factor here, an x factor here, and I have a log with this argument, the base of the log and the argument being the same. So my k equals log base e of 2/10. Did you figure out the pattern now? Okay. Your k value is going to be the log of whatever base you want and whatever base you have. Do you see that? So your k value ends up being the log of whatever base you want, and the argument is whatever base you already have. So when you write that expression, your new function, I'm going to call it g of x again, is e to the x log base e of 2/10. And there.